Okay, so now let's proceed. So in video 1, I have explained that the definition for elasticity is the ability of a material or an object to return to its original shape and size when force applied to it is removed. So why does that happen? So you can see that in elastic objects, there exist two types of forces, which are attractive forces and repulsive forces. So what happened, we compress a solid. Here I have a diagram. A hand is compressing a sponge. So what happened to the molecules or to the atoms inside the sponge is when we compress the solid, the atoms will move closer to each other. So when they are closer to each other, repulsive force between the atoms will act. Okay, so the repulsive force will act to oppose compression. So once we release the force, we release the sponge, it will return to its original shape. So on the other hand, when we stretch solid here, if we stretch the rubber band, the atoms or the molecules in the rubber band will move away or further from each other. So here, attractive force between the atoms will act to oppose stretching, so that the molecules can move closer back to its original position. So it will return to its original shape when we release the force. Okay, so here's the graph here. On the y-axis, we have forces of repulsion and forces of attraction. On the x-axis, we have distance of separation between two molecules. So when we do not exert any force on the object, the forces are said to be equilibrium. They are in balance. But what happens if we compress objects? So here, if we compress objects, we know that the separation between the atoms will decrease. So the separation here will decrease. And what happened to the forces of repulsion? From the graph here, you can see that the forces of repulsion will increase as the distance between atoms decrease. Okay, next, what happened if we stretch solid? So you know that the atoms will move away from each other. So here the separation will increase, and you can see that the force of attraction will also increase, but in the opposite direction. It will increase to oppose the change. Okay, so what happened if we stretch the object greater than the one that I am drawing here? Okay, so this is called elastic limit. So if we stretch using a force that is greater than elastic limit, you can see that it does not follow the rule just now. So the forces of attraction will no longer increase because the object will break. Okay, so now let's do exercise on problems involving arrangement of springs. So in many daily applications, like in motorcycle, in baby cradle, and so on, we can see that we have springs arranged in series and also springs arranged in parallel. Okay, so to compare the differences between extensions of springs in series and springs in parallel, we need one standard spring first. Okay, so here I have one spring in which when I place a load of 2 Newton, it will extend by 2 centimeter. So when I increase the load to 4 Newton, you can guess that the extension will increase to 4 centimeter. If I increase to 8 Newton, the extension will increase to 8 centimeter. It's that simple. Okay, so now what if I have two springs and I arrange the springs in series? Okay, so here I have two identical springs, the one similar to this one, but I arrange it in series. Okay, so here for each spring, it will extend by 2 centimeter. Okay, so let's say I place a load of 2 Newton. So you know that here if I have one spring, extension is 2 centimeter. So when I arrange in series, so each spring will extend by 2 centimeter. X1 will extend by 2 centimeter. X2 will also extend by 2 centimeter. So the total extension of the system, now we have a system here. So the whole extension is 4 centimeter. Let's say I increase the load to 8 centimeter. Sorry, to 8 Newton. So we compare to the standard one here. For 8 Newton load, the extension is 8 centimeter. So each spring will extend by 8 centimeter. So the total extension of the whole system will be 16 centimeter. Next, what happens if I have two springs and I arrange the springs in parallel? So you can guess logically that if we have two springs arranged in parallel, the springs will share the load equally. So the weight of the spring will be distributed equally between two springs. Okay, so now the spring won't extend to 2 centimeter, but it will share the extension. Okay, so now I have 2 Newton load. So before this, if I have one single spring, 2 Newton will extend to 2 centimeter. But now the spring will share. So meaning that extension will divide by the number of spring. Okay, by the number of spring, it means that 2 divided by number of spring is 2. So extension is 1 centimeter. So here is 1 centimeter. Here is also 1 centimeter. But the whole system, the extension of the whole system is only 1 centimeter. Okay. So the extension here, we consider the extension in vertical. Okay. So let's say if I have 12 Newton load. Okay. So here, from the standard one, if I have 12 Newton load, the extension is 12 centimeter. But since I have two springs arranged in parallel, so 12 centimeter or the extension divide by the number of spring 2, so you will get 6 centimeter. If I have 3 spring here, so the extension will divide by 3. I have 4 divided by 4 and so on. Okay, so here I have one SPM question. So this is SPM 2011 question. So you are given 3 diagrams. X is arranged in series. Y and Z are combination of series and parallel. So here you are not given the load, you are not given the extension. So what you can do here is you can assign a value. For example, one spring will extend by 2 centimeter when load of W is attached to it. Okay, so X, Y, and Z are attached with an identical load. Probably 2 Newton, 3 Newton, but it doesn't matter. Okay, so here you can calculate one by one. So for series, X1, X2, and X3, each will extend by 2 centimeter. So the total extension of the whole system is 6 centimeter. For Y, we have parallel and series. So for the parallel part, the extension is 2 divided by 2, so it is 1. And for the one single spring below it, extension is 2, so the total extension is 3 centimeter. Z is actually similar to Y, so the total extension is 3 centimeter as well. So now you can write the relationship. X is the biggest, so X is greater than Y, X is also greater than Z, and Y is equals to Z. So the answer is C. Okay, so for the last part of this subtopic, it is the factors that affect spring constant. So here I have 4 factors affecting the spring of constant. Let's take a look at the first one. Okay, so if you have a short spring and a long spring, which one is more stiff? Okay, so here stiffness is, if you have a stiff spring, it means that it is harder to extend and compress spring. So obviously, short spring is more stiff. So if you conduct Hooke's law experiment using a short spring, you will get a steep graph. Okay, so the blue graph here is indicated by the short spring. It is more stiff, it has high spring constant, and the graph is more steep. So for long spring here, it has low spring constant, meaning that it is less stiff, it is easier to extend, and it is easier to compress. When you conduct an experiment using a long spring, you will get a less steep graph, which is less steep, the one indicated in red. Okay, so next factor is the thickness of spring. So I have thick spring P and thin spring Q. So you can guess that a thicker spring is more stiff. So P has high K, high spring constant, and more stiff. If you draw a graph, you will get a steep graph. So this is P. On the other hand, for thin spring, it has low spring constant and less stiff, as indicated by Q. Okay, next factor is diameter of the spring. So P is a big diameter spring. So big diameter spring is actually easier to compress and easier to extend. So we say that it has low spring constant and less stiff. Oh, sorry, this should be X here. So less stiff has less steep graph. Whereas for a small diameter spring, it has higher spring constant, it is harder to extend and harder to compress. So it is more stiff and the graph is more steep. Okay, so the last one is type of material of the spring, which is steel and copper. So we know that steel is a stronger material. So P is actually more stiff compared to copper. Okay, so more stiff, steel, the graph of steel will be more stiff, high K, high spring constant. Whereas for copper, Q here, it is less stiff and low spring constant, which is less steep. Okay, so I think that's all for subtopic 1.4 elasticity. Hope you can do more exercises to understand this topic. Thank you.